Okay, were there any questions on that the solutions chapter? No, because we're going to move on to the next chapter, which is acids and bases. And so this is chapter 17, acids and bases. Let's just take a look at acids again. What's the strongest acid on the chart? HI, hydroiodic acid. What does it mean to be a strong acid? What it means to be a strong acid is it easily loses the H+. Easily loses the H+ because these are the conjugate bases, because iodide has very little pull for H+. And what that means is it's weak, it's negligible ability to remove protons, so iodide really doesn't have a strong attraction for that H+, and therefore they can dissociate. In fact, all these anions are so weak, we don't really think of these as being bases. And so strong acids are going to have extremely weak conjugate bases. However, weak acids are going to have much stronger conjugate bases, so these do have a pull for H+. And so what happens is, okay, HSO4 could lose that to form H+ in sulfate, but sulfate has some residual attraction for that. And so this base is not so weak, not so terribly weak as these. And so as we go down the list here, we just see it here, like this. Does hydroxide easily lose an H+? Does hydroxide easily lose a hydrogen? No, it's very difficult for hydroxide to lose a hydrogen. If it loses a hydrogen, what does it form? It forms oxide. Oxide has a powerful attraction for H+. In fact, oxide is the strongest base on this chart. On our chart it's different. But this strong bases will have a strong attraction for the H+. Therefore, they don't lose them here. So these would be extremely weak acids. And so the first thing that I want to talk about, you know what? I'm going. Is it okay if I go? I wasn't going to follow the PowerPoint for this one. Or do you guys like the PowerPoint? For the PowerPoint? You like? Okay. We'll go with the PowerPoints, because I was going to jump into something else first. But these are the acids here. We'll just follow the PowerPoints. And so we have three definitions about what an acid is. One is Arrhenius. Arrhenius just says an acid is a substance that gives H+ solution. In fact, acid is just H plus AQ. Arrhenius, acid is H+, Arrhenius base is OH minus. Or H plus and OH minus. But it turns out it's too narrow. This is Arrhenius base, OH minus. So Arrhenius, H plus and OH minus. Then we have Bronsted. Bronsted is H plus donor or H plus acceptor. And so base this is probably better, H plus remover. Base is pluck H's off. So this base is going to try to pluck this hydrogen off water. The acid is H plus loser, donates it. And so this would be a Bronsted acid-base reaction. Bronsted acid-base we don't have to deal with like Arrhenius. Arrhenius acid-base reaction, there's only one. What is an Arrhenius acid-base reaction? Arrhenius acid-base reaction is H plus and OH minus. That's all we can say. But this one does this fit the Arrhenius definition? H plus and OH minus? Is that what we're reacting? No. And so this is a broader definition. H plus and OH minus still fits the Bronsted, but this encompasses more acids and more bases. And so in this case, this base attacks the acid. Normally we say the base attacks the acid. This is negative, that's positive, so this negative is going to try to pull off that proton. Partial positive, partial negative. It's polar. If it's successful, then we form ammonium and hydroxide. Now, is there a driving force for this particular reaction? Ammonia plus water yields ammonium and hydroxide. Well, the driving force is going from stronger to weaker. So we're going to go from stronger base, ammonium, to weaker base, hydroxide. Is that stronger to weaker? No. this is weaker to stronger, so we're going from a weaker base, ammonia, to a stronger base, water. And likewise, water. Water is a weaker acid than ammonium. So there's no driving force. So if there's no driving force, does that mean there's no reaction? Well, it depends on how uphill this is. This is no driving force, so this is uphill in energy. But if it's not too steeply uphill, we could have partial reaction occur. And that's exactly what happens here. We get partial reaction occur. It's somewhat steep, so there's very little of this product. When things are extremely steep, we get no reaction. Here we get partial reaction, partial reaction, partial reaction, partial reaction, 100% reaction. Straight shot downhill. Does that make sense? And so it depends on how big of a difference it is. Well, let me tell you, there's not, in other words, if I had 100 of these, about one would form this. And so in other words, ammonia and water can react in metathesis reactions. Ammonia and water can react in metathesis reactions because it generates a little bit of hydroxide. Ammonium is very unreactive in metathesis because all ammonium salts are soluble. But hydroxide is much more reactive because not all hydroxides are soluble. Most hydroxides are insoluble. And so this tends to precipitate a lot of metals. And so ammonia will, or potentially can react in metathesis. That's Bronsted. And then there's one more definition, Lewis. Lewis is the broadest definition. And so what we could do is we could just throw the Arrhenius definition into the garbage. The Bronsted definition can be thrown into the garbage, and we just keep this one, the Lewis, because Lewis is the all-encompassing definition. Did I already talk about this? The Lewis is all-encompassing. But the problem with the Lewis is it's too complex, because when you want to understand Lewis acid-base reactions, you know what you have to draw? You have to draw Lewis structures to understand these. And so they're a bit more complex, like this here. This is what we call Lewis acid, this is Lewis base. So ammonia is both Bronsted base and Lewis base, but non-Arrhenius base. Do you see ammonia is non-Arrhenius base? It doesn't have hydroxide. It can form hydroxide, but it doesn't have it. And so here, in this case, the ammonia is an electron pair donor. And so here the base is going to attack the acid. So this electron pair, this orbital here, this is the orbital, is going to be donated here, form bond. This is what we see here. This is a very interesting molecule, but the reaction that happens there. And so Lewis reactions are a little bit more complex, but we have these three. This is the summary of the acid-base theory. And so we retain the last two. Bronsted Lowry because it's easy. Lewis because it's all encompassing. More difficult. So we need these. Let's take a look at two Lewis acid-base reactions here. Let's say I want to do this reaction, carbon dioxide and water. Carbon dioxide, this is what we call Lewis acid. This, it could be either an acid or a base. In this case, it's going to be a base. And so the first thing in this is we need to draw out the Lewis structure. So we'll draw out the Lewis structure for CO2. And then we'll have water. Draw out the Lewis structure for water. And then what we do is we look for positive and negative parts of this. And so as far as CO2 goes, the oxygens are negative, so delta minus. The carbon's positive. If we look at the water, the oxygen's negative, the hydrogens are positive. And so what are our potential reactions here? One potential reaction is this. One potential reaction is this negative oxygen reacts with this positive carbon. The other potential reaction is this reacts with this. So it's 1, 4, 2. And so this requires some playing around with here, but it turns out that 2 is a dead end. 2 is a dead end if you do some trial and error. And so we're going to go with 1. If we proceed with this route, then a base is electron pair donor. An acid is electron pair acceptor. And so what happens here is this. The oxygen on water is going to come in here. This. And this lone pair here is going to be converted into a bonding pair now. So this lone pair comes in here, bond. But can carbon have 5 bonds? No, so what we have to do is we have to kick out one of these. Let's kick out one of these here, like this. So what we end up with is a structure that looks like this. Okay, does that structure look stable to you? Does everything have an octet? Yeah. Everything has an octet, but what's not stable about this structure are the formal charges. We end up generating a positive formal charge on this oxygen and a negative formal charge on that oxygen there. And so that's not stable. One oxygen loses, the other gains. Doesn't sound stable. And so what can happen is this. There are vibrations in this molecule. And one thing that can happen is this. If that oxygen has a positive charge, it makes it much more electronegative. The typical electronegativity of an oxygen is around 3.5. But a positively charged oxygen is going to have much higher net electronegativity, which is going to suck electron density away from this hydrogen, making this hydrogen much more acidic than normal. And so this hydrogen is going to build up a positive charge. If that hydrogen builds a positive charge, then what happens is this. There's vibrations. This is called an intramolecular proton transfer. And so what we're going to do is we're going to transfer a proton within the molecule. That's why it's called intra. And so what we're going to see here is an acid-base reaction occur within the molecule. This is basic, that's acidic, boom. This takes that hydrogen and plugs it off, and then we end up with this structure here. The structure that we end up with is going to look like this. That bonding pair is going to be converted into the lone pair, and this lone pair is going to be converted into the bonding pair. So we're going to bond this, break that. So we end up with this. You know what this is? This is H2CO3. H2CO3 is called carbonic acid. So if we take CO2 and water, we can form carbonic acid. Now, does this look like an easy path to take? No. And so it's actually more favored this way. In fact, carbonic acid is not stable. Carbonic acid decomposes into CO2 and water. So this is an example of a Lewis acid-base type reaction. And if you think about it, what's easier to deal with, Bronsted-Lowry or Lewis? And Bronsted is way easier, but we're going to miss this because this is not a Bronsted type reaction. And so for Lewis, we look for electron donation and electron accepting. But nonetheless, if it's an acid, then acids, what they do is they make water more acidic. You know, if you put acid in water, it's going to make more H plus in water. And this is what we call an indicator. Indicator is a dye that changes color depending on how acidic or how basic the solution is. And so the more acidic this is, this cabbage dye turns this color. The more basic, it turns this color. This is an intermediate color. Red and yellow make this blue, green color here. That's the red cabbage. This is coral and acid. In acid, coral is made up of carbonates. Carbonates and acid form carbonic acid. Carbonic acid decomposes into CO2. So this is a piece of coral being attacked by acid. This is zinc being attacked by acid. When zinc gets attacked by acid, it forms hydrogen gas. Those are Bronsted acids. So those are characteristics, some properties of acids. So when we do acid-base reactions, we have to do this conjugate thing to get the driving force. Remember the driving force? We're going from stronger to weaker. So we've already been doing this conjugate thing. You know, we find the acid and base going forward, we find the acid and base going reverse. And we pair them. The acid is paired with the base paired with the acid. So the base is B, the conjugate acid is HB. The acid was HA, the conjugate base is HB minus. That's what we see in the acid-base chart of the conjugate pairs. So here is their driving force for this. So the acid here is acetic acid. The base here is water. You know, the base is the H plus remover. And it forms hydronium. And so what we have is the base, water, has a conjugate acid to hydronium. The acid, acetic acid, has a conjugate base acetate. And then we compare. Which one's stronger, acetic acid or hydronium? Hydronium's stronger. Which one's stronger, water or acetate? Acetate's stronger. So we're going from weaker to stronger, which says no reaction. But it turns out this is not terrible. And so we get a little bit of reaction here. And so we come up with this scheme, which we'll talk about in a minute. So what is the conjugate acid of ammonia? The conjugate acid of ammonia is, well, if ammonia is the base, then the acid would be, you add H plus, and the acid is ammonium. What is the conjugate acid and the conjugate base of bicarbonate? That's a little bit more tricky here, maybe. What is the conjugate acid of bicarbonate? Well, acid, you add an H plus. It would be carbonic acid. Base, you remove an H plus. It would be, this is wrong. Oh, no, this is right. Acid is carbonic acid. What's the base? Carbonate. Carbonate's the base. Bicarbonate's amphoteric. That's why it has this, two of them. Ammonia is also amphoteric. Its conjugate acid is ammonium. Do you know what the conjugate base of ammonia is? Amide. Amide would be the conjugate base. So the strength of acids and bases, you know, strong acids ionize completely. This is the pattern. So strong acids ionize completely because there's a huge difference in acid strength and base strength. Well, maybe not. So strong acids ionize completely, weak acids slightly ionize. Strong bases hydrolyze completely. Weak bases hydrolyzing completely. And so let's look at acid in water and base in water. This is what we're talking about. This is how we determine the strength of the acid and base. So acid in water. So acid in water, there are two ways we can do it. We can say ionize. HCl ionizes into H plus and Cl minus. It's strong. So, you know, strong means it goes to complete. A weak acid weakly ionizes. So if I look at acetic acid, it partially ionizes. So since it partially ionizes, I'm going to write a reverse arrow here too, going H plus and acetate, like that. This is weak, and so it's not complete. In other words, it's partial ionization. Strong is complete, weak is partial. All right, the next thing is this. In reality, I don't know if you remember this, but is H plus stable? No. Why is H plus not stable? H plus is not stable. Anybody remember why? It's pretty hard because it's probably back in chapter 1 or chapter 2. We're talking about coulombs. It's because of its size and charge. It's a huge charge to size ratio. So if H plus is in the presence of water, it immediately forms hydronium. And so in our hydrolysis reaction, we just take HCl plus H2O. HCl is the acid, H2O is the base. And this is going to hydrolyze to form hydronium plus chloride. These two reactions are the same. The ionization and the hydrolysis reaction are the same to chemists. It's just easier to write the ionization because it's less work. And the same thing. So we have complete hydrolysis. For a weak acid, we have partial. So HC2H3O2 is partially going to hydrolyze water to form hydronium a little bit and acetate a little bit. And so it's about 99%, 99.9% this, 0.1% that. And so this is incomplete or partial hydrolysis. And that's how we define strong acids completely ionized or completely hydrolyzed, weak acids partially ionized or partially hydrolyzed. Now bases don't do this. Bases do something called hydrolyze only. And the hydrolysis looks a little different. And so something like sodium hydroxide. Sodium hydroxide, we consider that a salt first. And salts, like this, ionize. And so soluble salts ionize 100%. And then once we this is the base. And so strong base is hydrolyzed. So hydroxide plus water. Hydroxide plus water yields water plus hydroxide. So strong bases hydrolyze completely. How about a weak base? A weak base does not hydrolyze completely. And so let's compare sodium hydroxide with sodium carbonate. Sodium carbonate would be a weak base. First thing is it's a salt. It's a soluble salt. So this is going to form 2 sodium ions and 1 carbonate ion. The carbonate is the base. So what do bases do? Well, is it a strong base or a weak base? It's a weak base. If it's a weak base, then it partially hydrolyzes water. And when it partially hydrolyzes, it's going to take an H plus off water, formed by carbonate and hydroxide. So this is partial. So weak bases partially hydrolyze. Weak base is partially hydrolyzed. And so some people will get it confused because they'll see, oh, sodium carbonate that completely ionizes. But it completely ionizes because it's a soluble salt. Soluble salts completely ionize. But carbonate itself is a weak base. And that only partially hydrolyzes. Bases do not ionize. Bases do not ionize in water. They hydrolyzed. So here's our chart of acid and base strength. And there's also the conjugate pairs. List the following acids in order of decreasing strength. What do you think? Just take a guess. Let's see how well you. Phosphoric acid is strongest, yeah.
And then
Well, it's not carbonic, it's hydrogen oxalate.
oh,
Hydrogen oxalate versus ammonium, what do you think? I would think ammonium, I mean, it's positive, whereas hydrogen oxalate is an acid anion. But we could take a look at the chart. We look at the chart, and this will you given the chart probably, but here's phosphoric acid here. Go down the list. Here's a hydrogen oxalate here. And here's ammonium here. And so it was hydrogen oxalate. And you might have guessed it might have been hydrogen oxalate. It's a little bit unusual because I would have guessed ammonium and then hydrogen oxalate. But hydrogen oxalate is a little bit unusual because hydrogen oxalate comes from oxalic acid. And oxalic acid is the top weak acid here. It's borderline strong. And so that's why. And the other thing is HSO4 minus. HSO4 minus comes from the acid H2SO4. And HSO4 minus is one of the strongest weak acids, just like oxalic. I mean, oxalic is, and so that one's not really a good one. I wouldn't have given that one because that one it's not clear, unless you have the chart. If you have the chart, then no problem. It's easy. But I would have guessed ammonium before hydrogen oxalate. Well, when we're doing acid-base reactions, Braun said, we predict it by looking for a driving force. What is the driving force? Going from stronger to weaker and stronger to weaker. I don't, this diagram I don't really understand so well. Oh, I get it now. They wrote the reactants in pink and the products in blue. So that's why it looks funny. Okay, next one we have here is favorite acid-base reaction. Why don't you do this one here? Okay, so we're almost out of time here. Let me just end with this. We have hydrofluoric and sulfide ion. And so hydrofluoric is acid only, sulfide is base only, based on the chart. And so the only potential reaction here is that HF loses the proton to sulfide. We end up with chloride and HSO3 minus. And then we just compare. You know, in the forward direction, HF loses the proton. In the reverse direction, HSO3 minus loses the proton. So they screwed this up. Do you see the error here? This is right. HF's the acid going forward, sulfite's the base going forward. But going backwards, this can't be right because fluoride doesn't have any H to donate. Acids are H plus donors. And so they got this backwards. And so what we're comparing is we're comparing HF versus HSO3 minus. You don't have to have that memorized, we just look at the chart. HF versus HSO3 minus. When we look at in the chart, it turns out that HSO3 minus is weaker than HF. So we're going from stronger to weaker, therefore there's driving force. So this should favor products. But how much stronger to weaker? If it's like this, then we say it's complete reaction. But if it's like this, then we get partial reaction. It's downhill, but it depends on how steep downhill it is. So this is what they mean by equilibrium. At equilibrium, you know, if it's just partially downhill, then there could be a little bit of leftover product here. There's a comparison of acid base and redox. You know, acid base we transfer protons, redox we transfer electrons. We have acids and bases, we have reducing agents and oxidizing agents. We have things that are amphoteric. They can act both as an acid in one reaction and a base in another. The same thing. The same species can act as an oxidizing agent in one reaction and reducing agent in another. It depends on what you react with. It's stronger. Acids and bases can be classified as strong and weak. Oxidizers and reducers, the same thing. And the predicting driving force is stronger to weaker in both. Okay, that's the first part of acids and bases. The second part deals with pH. So let me talk about that next time, tomorrow. Talk about pH. I'll end it now.